Tonight, our guest presenter is a fellow that is not entirely new to the club. He worked with the Makers Group when we did the software-defined receiver. His name is Barry Duggan, so he knows Vienna Wireless. He is a terribly talented fellow, graduate of Georgia Tech, electrical engineering, career computer programmer, specializing in real-time control data communications and security. He's got amateur radio license since 1953. Started working on the GNU Radio project, and that's GNU, and is where basically you build a radio using software. No, not much hardware required. He supports that project, so he's the pro in the GNU Radio movement, and we're thrilled to have him.
Well, thank you. I'm glad to be here, and I'm going to do a presentation on using GNU Radio, which is a software package to create software-defined radios with almost no hardware involved. I'm an electrical engineer from Georgia Tech, career in real-time computer programming, and learned about GNU Radio in 2019 and was really excited that I could combine my amateur radio interests and my computer programming career and create radios with programs. GNU Radio is free and open source software development toolkit that provides digital signal processing blocks to implement software radios. In other words, this is all computer stuff. There are over 550 functional blocks to do things like modeling a noisy and fading transmission, performing QPSK encoding and decoding, doing complex filtering, and so much more, just about anything you want to do in a radio. So there's a graphical user interface to support easy creation of flow graphs to connect the blocks into a complete executable program. You can test the design with built-in tools, and if you find things you want to change, the revision and retest cycle is easy and quick. So within minutes or an hour or whatever, you can come up with a design, test it, go back and make changes, test it again. It's very, very easy. And until you get into the real world, there is no hardware required. Okay. Hardware required. The RF front end is the only piece of hardware that is necessary in this design. So we've got an antenna feeding an amplifier, and on this upper path, we've got a local oscillator multiplying that signal and then filtering it and going into an analog to digital converter. So the output of that we call the in-phase signal from the device. And then in the other path, we're taking the local oscillator and phase shifting it 90 degrees and multiplying this input signal by that and filtering it and doing another analog to digital conversion. And we call that the Q signal for quadrature. And these I and Q signals are what we process in the software of the design. What is sample rate? The sample rate is how many data values are produced per second. So for a complex data stream, both I and Q values are present. For example, a sample rate of 2,048,000 samples per second produces that many data points per second, which is a lot of data. So let's build a radio. The RF front end can be as inexpensive as $20 with everything else done in software. And that's what I'm using for the demo, is the bottom end of the line of devices. So let's take a look at a tutorial about how to build a broadcast FM receiver. Okay, this tutorial starts with the basics and walks through every step of putting together an FM receiver. So the first step is to create a new flow graph. So I'm going to go here, and there are two ways of doing this. This little icon here is the simplest, and this creates a new canvas with just two blocks in it, options and a sample rate. So the first thing to do, so we're going to get a RTL-SDR source block from the SOAPy collection. SOAPy is a generic package that supports lots of different equipment and is very easy to use. So back to the flow graph, we're going to go over here to SOAPy, and we want a source, and we want a RTL-SDR, and drag that over here. That's how easy it is to get blocks in the flow graph. So the next step, it has to be configured for sample rate. So we are going to modify the variable called sample rate to that value. So we highlight the block, and I can either hit return, or I can right click it and go down to properties, and either one gets me back to the property menu. The sample rate is 32K. So let's say okay to that right now. We're going to go to the variable sample rate, highlight it, and we're going to change that to 2,048,000 and apply that, and okay. And notice that now that value has been brought down into the source plot. Now there are two things we need to set up to control this. So back to the tutorial here, we need to define a frequency, and we need to define the gain. So we're going to get two range blocks to do that job. And we go back to our flow graph here. We go to GUI widgets. By the way, if you can't find, if you don't know all this by heart yet, you can actually go to the magnifying glass here and tell it what you want to find, and it'll find it for you. So we need two range blocks here. There's one, and there's two. So now in this first one, we're going to set it up for frequency. So the tutorial says to set all these parameters, and then it shows a picture of what it's going to look like while you're doing it. So let's go back and do that. So I can click it here and do that. The ID is the name of the variable that we want to define, and we're going to call that FREQ, and we're going to label it center frequency. And the default value will be, he's using 88.5. I'm going to use 101.1. And this is a local FM radio station that I'll be using to demonstrate. So in the US, the start of the FM band is 87.7. And this is scientific notation. You can either use scientific, which is easier to type, or you can use the entire integer value. But who wants to do all that? Okay, the top of the FM band in the US is 107.9 P6, and the stations are spaced out 200 kilohertz. Okay, now GUI hint is a strange concept, but basically if you picture drawing a grid pattern of rows and columns, this is telling the program that lays out the actual display what rows and columns you want to use. So if you don't specify anything, it decides where to put it. But we're going to say row 0, column 0, 1 row wide, and 10 columns wide. That's what those 4 numbers mean. Okay, so now we've got this GUI range block filled out, and we'll go on down to the next. We're going to set the gain. So we'll do it the same way. Go back to the flow graph, pull this over where I'd like it to be. And the ID of this will be RF, capital DAIN, and the label is going to be RF in, and that's in dB. The default value is going to be 10. Start at 0, stop at 50, and step will be 1. And we're going to put this in row 1, column 0, 1 row wide, 10 columns wide. So now we've got the RF gain set. So now we got to tie those together with the SOFI source. So we're going to go back to that, and in the tab for RF options, we're going to set the frequency and the gain RF options. Frequency is already the default name for that. RF gain, instead of being a fixed number, we're going to use RF gain variable. So now this range control sets the frequency, and this range control sets the gain. Oh, I see one thing I didn't do. Let me go back and do that real quick before we proceed. In the options block, there's a couple of things that need to be set up. So let's go ahead and do that. Okay. Default is not a valid name for a flow graph. So we're going to call it RTL_SDR_PRES for presentation. Now I'm going to use this 2 more places, so I'm going to copy it using a keyboard, Control-C, and then go down here and paste it there, keyboard, Control-V. And all this is okay, so let's apply that. And then let's save it before we lose it. We go to File, and Save As, and I have a working file folder called grdev. So I'm going to put it in there. And this is already highlighted. So if I just do one more paste, there's my file name. And GRC is for GNU Radio Companion, which is this GUI. So we'll save that. So that changed the name up here. Okay, let's carry on here with the time and frequency plots. With software-defined radio, you cannot stick a scope on a test point in there in a literal sense, but you can look at data points and see the equivalent functions. So we're going to use a frequency sync and a time sync. So let's go get one of each. And they're not under widgets, they're under instrumentation UT. So here's a frequency sync, and here's a time sync. So we'll stick this up here. I'll stick this one here. And let's look at the properties for that. And okay, center frequency, we want to be FREQ. And the bandwidth will be the sample rate. And I think that's all we need. And we can take this output and feed it into that input. And then both of those blocks are happy because they're connected to something. So let's do the same thing with the time sync, AKA oscilloscope. And we don't need to change anything on that, so we're okay. So let's connect this output to the time sync. So in our tutorial, we now have something that looks a lot like what I built. And we can actually run it at this point. It's going to go to that broadcast FM station, and it will show these plots. And all you have to do to run it is to come right up here to the execute flow graph, and this is what you get. Now, the layout was based on those numbers I put in. And so we got the frequency, both with a slider and with numbers, and the gain. And this is the amplitude, which is the I and Q traces. And this is the frequency plot. And you can tell this is a stereo station because this right here is the left plus right, which is the main content. And then we'll just see them better in a minute. Let me crank the gain up. Give it some more here. Yeah, that's good. So these sidebands contain left minus right. So if you take the main content, which is left plus right, and you add the two together, you get only left. And if you subtract the left minus right from the main channel, you get only right. And that's how stereo sound is created. But there's no sound here yet because we haven't done anything to produce sound. Okay, back to our tutorial. And it looks like that, except mine was better. And they cranked up the gain. Okay, now at this point, the reason I generated this flow graph is this is our RF front end for what we're doing tonight. But just to show you what happens if you follow through with the tutorial, you will get this flow graph. And this is the completed just like step by step the way the tutorial said, including the stereo add-on that I put in there. So if we run this, here is that station, and it's got some sound. I have the volume off right now. So I'm going to give it a little bit of volume.
Of the population claim to believe in God.
It's a Christian radio station, but at least you can see that it is actually functioning properly. Okay, so we have this as our RF front end, and I just showed you the completed flow graph for the tutorial, and this is the part that we're going to use for the continuing. Now let's go back to the slides a minute. Okay, single sideband. I'm going to have a demo that shows what sidebands really look like for upper and lower sideband. And then I'm going to talk about offset tuning versus direct tuning. And then I've got another flow graph to show you. But first, I want to show you the flow graph for this demo. Here is the flow graph for the demo. This section, middle section right here, is a single sideband transmitter with no hardware involved. This is a simulation. So the signal coming out of this virtual sync right here is the transmit signal. And that is virtually connected to here. Instead of those two blocks of sync and source, I could have just taken this output and connected it down here, but this makes a prettier layout, easier to follow what's what. And this lower line is the single sideband receiver, which we will revisit in a little bit. Okay, now I have a recording of the demo, and that's because I needed a separate microphone. Anyway, it got complicated, and so I made a recording. To get a better idea of what sidebands look like, I have some visualization to show you. And as you can see from this, the energy frequencies are all positive or above the zero. And the waterfall shows the same down here. So now if I switch to the lower, you can see that all the frequency, all the frequencies are below zero, and the waterfall shows the same here. Reason I didn't have the receive the same as the transmit is I'm hearing myself in my headphones, and it's delayed enough that it makes me stutter, which isn't good. So there's lower, and there's upper. 1, 2, 3. And there's the flow chart for it. Back to the complex data from coming out of the analog to digital converters. I and Q together create what's called a complex value. And in that world, frequency isn't just from 0 to infinity in the positive direction. 0 becomes a baseband, basically where you are tuned at the moment, and anything positive is a higher frequency than your 0 reference or baseband, and the negative frequencies are frequencies below your 0 point. I have some illustration for that. Okay, we're going to use a frequency translating FIR filter, frequently called a FIR filter. Here's 0, where you're tuned at the moment, and you're interested in this orange signal over here on the right. Now with direct tuning, you would just tune over to that signal and make that around 0. But for single sideband, changing the tuning of these dongles can be disruptive. And if you're only changing your frequency, say 100 hertz at a time, trying to get zeroed in on the station you want, it becomes very ragged. But there's a better way. Using this frequency translation block, we can stay tuned here and bring this signal to 0 through the software. So that's the main function of this block. But then we can also do some filtering to get rid of these other guys and have only the signal we want. And then one more function is called decimation, which is a change in the sample rate or decrease in this point. Decimate means to decrease. And so we're changing this wide band signal here to a much narrower one centered around the desired signal. Here is the flow graph with the translating filter and also decimation of 4, which means our input rate was 1.92 megasamples. If you divide that by 4, you get 480 kilosamples per second. And then we're feeding that to a resampler that will decimate some more by 10. And its output then will be 480 kilohertz, which just happens to be the audio rate that we use in the system. This is a demonstration of actual transmitting and receiving over the air using single sideband, upper sideband on 2 meters. I've started the tuning about a kilohertz low, and then we'll tune upward towards the received signal. That's usually the way I end up doing it online for real. Kilo Victor 4 Foxtrot Victor. As you can hear, I need to go. Kilo Victor 1, 2, 3, 4. That sounds about right. Kilo Victor 4 Foxtrot Victor. That's one. Yeah, that's better. 1, 2, 3. Okay, how to receive single sideband. Back in February, I did a presentation to the makers group. They had built a piece of hardware that was the RF front end. And so to support their efforts, I created a single sideband receiver to take that signal and make a complete receiver out of it. So putting them together, there's the receiver I built for the makers, and it produced audio, which I converted to left and right. I converted to complex, and then that's my receiver. And this is a complete unified receiver. Now, very quickly, how to receive HF. It turns out these dongles in what I choose to call normal mode go from 22 megahertz or so up to about 2.2 gigahertz. But they have an alternate way of receiving those signals called the direct sample mode that goes from 500 kilohertz to 24 megahertz. So you've got the whole HF band covered with that. And most of them will do that change automatically, but the cheapie that I'm using, you have to give it a command to tell it you want direct sample mode. The other approach is called a ham it up, which is a little board you could buy that takes the input signal and adds 125 megahertz to it. So 40 meters appears as 132 to 132.3 megahertz. And it also gives you a low noise amplifier. So then you can receive it with anything that operates in the VHF band.